today I want to continue the idea of the exterior derivative, and in principle show you how the idea of the exterior derivative defined for us is called the exterior algebra. And from the exterior algebra, we will proceed to define another map called the interior product, will allow us to write down another expression for the Lie derivative in a rather compact way. Okay, so when I left off last time, I was showing you that there was an isomorphism, a vector space isomorphism between the set of R forms on the manifold and a set of n minus R forms on an m-dimensional manifold. But this is going to be important for us because it's going to allow us to define a map between the set of R forms and a set of m minus R forms called the Hodge-Star operator. And the Hodge-Star operator will allow us to rewrite many things that we're already familiar with. For example, the Maxwell equations, a set of 4 coupled partial differential equations. We will write in a very compact way using the idea of the exterior derivative and the Hodge-Star operator. Okay. But just proceeding where we were heading, we now know that there's a map, this exterior derivative that takes between R forms and R plus 1 forms. We can use this to define the exterior product of 2 general forms. Some the exterior product is a map that takes us between R forms P and M to S forms M to the set of R plus S forms P. Explicitly, I have some omega R form and some, let's say, eta that is an S form. Then I define the exterior product of these two to be the following. The exterior product is an R plus S form, which means it takes R plus S vectors to real numbers. Omega which eta of V1 to V R plus S. So this is some collection of vectors. This is defined to be 1 over R factorial S factorial sum of commutations times P omega of V of P1 to V P R eta of V of P R plus 1 to V P R plus S. Where all of these guys are all in E of M, and I runs 1. Sorry, I don't know. Okay. Obviously, if R plus S is bigger than M, then one of these indices will be repeated. And if one of those indices are repeated in a completely symmetric thing, then it's identically 0. So if R plus F, so I can word product, I can exterior product any R form, any S form, as long as R plus S, and I'll get a non-zero answer in general, as long as R plus S is less than M. If R plus S is greater than M, then this is identically 0. Okay. So we need this number. So if so that's what I'm the property of the exterior product. 1 if R plus F is greater than M, then omega wedge theta 0. Let's see. 2 if I'm going to take omega to be an R form. Eta to be an S form. And let's say psi to be a Q form. So probably 2 is that omega tensor, omega exterior product with omega is equal to 0 if R is odd. 3 omega exterior product with eta is -1 times 1 to the RS times eta exterior product with omega. And then omega exterior product with eta exterior product with psi. Same thing as omega with eta with psi. I'm going to leave it as an exercise for you guys to show these properties. The exterior product, this wedge product that we've got here, defines for us an algebra, or the exterior algebra. The exterior product defines an exterior algebra. That all differential forms M at P And this can be written as a direct sum over the set of zero forms, which remember this smooth functions. Set of one forms. All the way to a set of m forms on the m dimensional manifold. Here dimension. And the set is closed under omega. Sorry, under the wave product. So the reason for this is, if you go back to an introductory course in algebra, you remember that given a set of vector spaces, let's say V naught to Vn, the direct sum of those vector spaces is the vector space of all integrals V little v. Okay, let me write this. Just to elaborate what I said here. So, given set of vector spaces V1 to Vn, their direct sum V star V1 plus V2 plus Vn is the set of all vector space of all m integrals V1 to the end, with each of the VI lives in capital VI. And where we define addition and multiplication, scalar multiplication component-wise in the direct sum vector space. And the exterior algebra, this guy here, is just an example of direct sum vector space with the smooth functions. These guys, the infinity of them, taking the place of real numbers in constituting the composition, the linear combination of these guys. Okay. So the statement here is that omega p m star is an algebra over the set of smooth functions. On M, that is, it satisfies all the rules of an algebra except with smooth functions taking effect of real numbers. That's the field of what we define the algebra. And these rules for algebra state that if I've got one form, let's say omega sine theta, omega theta and psi, one forms, and f and g is smooth functions on the following exterior. That omega exterior product psi, sorry, omega plus psi is omega, so it's a community algebra. Sorry, it's not. This is omega plus psi plus theta is omega plus psi plus theta. Omega exterior product psi exterior product theta is omega psi theta. Omega psi plus theta is omega psi plus omega theta. Omega plus psi where theta is omega theta plus psi with theta. One that's omega S times G times omega is S D by multiplication of functions and omega F times omega plus theta is omega plus theta. And F plus G times omega plus G omega. Let me summarize terms of forms, their bases, and dimensions that they are.
Well, why do we say like omega star is the symbol in forms of n? We didn't write it as a direct sum of those, as a direct sum of those strips. Is the you have a set of differential forms, for example, to take the couple which you have like some one form that has some 2 points and 2 points and whatever, how do you think of that as a? Because the way you said it is so that it's the same all differential forms.
Yeah.
Like it's that in the sense of like a union of those spaces or
No, some collection of these spaces.
but then that would be just a couple, that would be any couple.
That's right, but one of those any couple is belongs in the set of different forms. So let me leave you to think about that. Continue, and we can talk about that.
So this algebra, right, is define a particular point
Yes,
P on the manifold.
that's right.
So what's the reason for using smooth functions instead of just like K and R if we just put on a point?
Sorry, say that again?
So since algebra is defined at a point P in N,
Yeah.
you replace our field instead of using R as our field, we're using the fourth module. We're using smooth function as a K.
Yes.
But what's the point? Because the smooth function point is just the real number anyway.
But the smooth function doesn't have here.
Yeah.
In the same way that I would have the set of reals, I would pick any real number instead of reals to take linear combinations. Point that I pick functions.
So it's just like a convenience, right?
It pretty much is, yeah.
Okay.
So these are R forms. This is the basis of those R forms. And this is the dimension. So for example, omega naught then is seen by the this is smooth functions. Basis is 1, dimension is 1, and set of 1 forms. It's the same as what we were calling TP star. Okay. So I'm not specifying the point here because this statement extends to all points in the manifold. But then I have to not talk about this as the tangent, the cotangent space at the point, but the union of all cotangent spaces at all points is called cotangent manifold. We'll get to that in a little bit. The point is that this thing is spanned by a set of objects that look like that, and the m set of objects with dimension this and the n-dimensional manifold is m instead of 2 forms. And no particular other designation, but these are spanned by objects that take the form dx mu, which dx mu. And I'm choosing 2 objects from a set of m objects like this. So the dimension of this is the half m 1. Omega 3, set of 3 forms, m basis dx mu, which dx lambda. There are 1/6 of m minus 1, m minus 2, these guys. This will go all the way up to the set of m forms on m. It's precisely one of these guys. And this is dx and by dx mu1 through dx mu m, and if you look at this, the dimensions go up and then you come back down again, paired up in a way that recognizes that set of R forms on M is isomorphic instead of F minus R forms on M. Vector spaces. Wait, have I talked about the exterior derivative? I feel like I was. Have I told you? Huh? Yes, now I can tell you about it. All right. So given an R form, omega, what we learned here is that we can build higher forms by taking their exterior product. But that's not the only way we can build higher forms. Another way to build higher forms is through a map between omega, the set of R forms, and the set of R plus 1 forms for the exterior derivative. So what I'm going to show you now is the exterior derivative map between R form and R plus 1 form is actually all the derivatives you know already bundled into one. So given an R form, omega you find the exterior derivative D map from R forms to R plus 1 forms. It takes an R form and it increases its degree by 1 to the following actions. So D omega so yes, omega is 1 over R factorial omega mu1 through mu R dx mu1 where dx mu R. Then the exterior derivative of omega, T omega, is 1 over R factorial d by dx mu, say, of omega mu1 to mu R dx mu, which dx mu1 with dx mu R. So if we start with an R form, we will end up with an R plus 1 form. And the fact that this is a wedge product automatically anti-symmetrizes this coefficient. So there's much more that I want to say about these forms, but let me just do a quick example to illustrate how this works and maybe give you some intuition for what it is we're actually doing. In particular, it looks very much like I've defined this in a coordinate dependent way. So I pick some chart, and if I can express omega in that chart with these coordinates dx mu and these coordinates x mu like this, then I can take the derivative and this gives me the exterior derivative. But in fact, everything that we can do in differential geometry, we can do in a coordinate independent way. I'll give a coordinate independent definition of what this thing is doing in terms of the actual maps. Just now, but I first want to just touch base with things that we know already. So suppose well, let's take manifold that we're working on to be R3. Then the canonical forms on R3, omega naught, 0 form is just function, and it's a function of x, y, z. So we'll take R3 coordinatized by x, y, z. Then instead of one forms are just functions of x, y, and z. Sorry, 0 forms of functions phi, x, y, and z. One forms all take the form some function of x, y, z dx plus some function b of x, y, z dy plus c of x, y, z. Right, so all one forms will be of this form, where a, b, and c are just functions. Instead of two forms look like this. Little f of x, y, z, dx wedge dy, g of x, y, z, dy wedge dz, and some h of x, y, z, dz wedge dx. And then finally, I have three forms, omega 3, that look like some maybe capital S of x, y, z, dx, dy, dz. There are no four forms in R3, because one of these guys, dx, dy, and dz, will have to be repeated by the symmetry property, wedge product, that would mean that 0. So let's see what D does acting on each of these guys in turn. D acting on omega naught is just d phi by dx. X plus d phi by dy, plus d phi z, dz. Okay, that's what the action of d on a 0 form is. You differentiate with respect to everything you can. You add in one more differential to that. So there are functions, or one more differential is one differential. What about d omega 1? And you can see that this is a one form. Okay. D omega 1. Skipping on steps here, but this is just dv by dx minus dA by dy dx wedge dy. So the couple of steps that I've skipped here is that when you first differentiate this first component with respect to y, you got dy wedge dx, and then I change that to a minus dx wedge dy. That's where this minus sign comes from. Okay, and then I will have this guy that I differentiate dv by dx, dx wedge dy. So I've got two things that looks like dx wedge dy. One will come with a minus sign if I with them in the same form. Okay, that's where these things come from, and that's where the minus sign comes. Next one is dc by dy minus db by dz. dy z, and then finally we have a dA by dz minus dc by dx dz which dx, and that's the two form. Then if I take the exterior derivative of the two form, that guy there, I get ds by dz. So I get df by dz because it will bring in dx and dy, and then I'll get a dz wedge dx wedge dy. I'm going to make everything into the form of dx wedge dy wedge dz. To do that, I have to exchange dz twice. Commute dz twice, and that comes with two minus signs, so that's plus minus, so that's this guy here. Plus dg by dx, and then I'll have a dx wedge dy wedge dz, plus dh by dy, and then I have a dy with dx wedge dz, and that's an even permutation. There. Overall, I have dx with dy with dz. Okay, and then finally, here the omega phi, any which way you cut it, taking any derivatives of this will introduce another one of dx dy or dz, so that's going to be 0. There are no 4 forms of the answer. Okay. So I already said that the exterior derivative encodes all of the former vector derivatives that we commonly div curl graph. Let me show you how this works in R, where you've done it before. So now I'm going to define the vector. Call it vector F, say. We're going to define the vector F to be a vector with components A, B, and C in the X, Y, and Z direction respectively, and by A, B, and C, I mean this A, B, and C, those functions. And the vector G to have components F, G, H, and F. G, H, and F, X, Y, and Z directions respectively. Then notice that d omega naught corresponds to the gradient of phi. This is obvious to see. Okay. Similarly, d omega 1 corresponds to the curl of f. So if I identify the components of the tree form, if I identify the components of the tree form of the x, y, and z components, then d omega 1 is nothing but the curl of f. And finally, d omega 2 This guy here is the divergence of G. So again, depending on the forms that you're differentiating, taking the exterior derivative to, the exterior derivative acts as the divergence, the gradients, the divergence, or curve. Okay. But in fact, there's more to be said on this example. For example, if I go d of d omega naught, d omega naught is this guy here. So let's take one more derivative. If I go d of d omega one omega naught, that's d of d phi dx, dx, d phi dy, dy, d phi dz, dz. Here I can differentiate with respect to y and with respect to z. So this is d2 phi by dy dx, dy which dx plus d2 phi by dz dx, dz with dx plus d2 phi dx, dy dx with dy plus d2 phi dz, dy dz with dy plus d2 phi by dx dz, dx with dz plus d2 phi by dy dz, dy which dz. And what we know is that mixed partial derivatives commute. So d2 phi by dx dy is the same as d2 phi by dy dx. I have a dy dx here. I have a dy dx here. In commuted order. So if I exchange these two to make a dy over dx, that will come with a minus sign, but this will stay the same. So this will cancel this. Similarly, this will cancel with this. Take this out. We will get 0. But we should have expected this because this is d squared acting on omega naught. We know that d squared is equal to 0. But what have we done from this that we didn't already know? But actually nothing because we need this again. This is the statement that, remember, acting on a one form, d acts like the curve. Which one form is this? Well, this one form is a gradient. So this statement that d squared omega naught is 0 is the statement that gradients don't have any curve. Nothing but the statement that curve of gradient is equal to 0. You can also show similarly that the second derivative also encodes the fact that the divergence of a curve zero by acting twice on g omega 1. So d squared omega 1 will pull out a similar relation, and you'll be able to use this factor. So again, all of this stuff we already know. What we've done is take it and cast it in a unified language where we don't have to talk about different types of derivative operators, divergence, gradient. They're all the same operators. They're all the derivative just acting on different rank forms. Okay, and similarly, a lot of the vector relations that you're familiar with from first year and second year calculus, vector calculus, are all encoded in this picture here. Right. The only thing is you're working in R3, and you have to fix the appropriate forms to work with. Okay, so let me stop there today. Okay, so I'm not sure why I think that I told you guys this already. D squared is 0. I haven't told you that already. Right. So what I've shown you, this example, is that two actions of D on form gives me 0. And in this example, it's 0 because mixed partial derivatives mute. You can see that, right? So I can identify the process. Now, in my definition, my core definition of what means that, you can see, if I take another derivative here, then I'll end up having to take two derivatives. So I'll get again partial derivatives, and I'll get two forms that I have to wedge into here. Those are going to be antisymmetric, those are going to commute. So the statement that D squared technically what we mean here is we should label the action of D, right? So D here, more technically R, it's an exterior derivative action on an R form. So the statement here is that D plus 1 dr is identically 0. This is a statement that the exterior derivative operator is, strictly speaking, 2 nil closest. If I square this operator, I'm going to get 0. Okay. Apparently, mathematicians work with higher powers. Okay. So this is a really important property of the exterior derivatives, and in fact defines for us a group called the homology group, and that homology group is dual to another group called cohomology group. The cohomology group is the group of things that are acted on by the operator that's dual to this guy, which is the boundary operator. We'll come to all of that now. There's one more point I want to make here, that I'd like you to keep in mind, and I'll define this more precisely when we go along. Forms are things that you integrate. So forms naturally live under the integral sign. Now, when you talk about an integral, if you wrote down something like the integral, technically, what we meant was the integral from A to B integral on the real line of some function dx, right? So this guy is a one form. And one forms naturally pair up with one-dimensional objects. What's one-dimensional object? This is an integral of R, technically called a chain. So forms pair up with chains to give you real numbers. In this sense, and because these guys live in a vector space, right? And these guys have all copies of the vector space, they're dual to each other. So forms are things that are dual to chains. So, you know, if you want to touch base with things you know from first year already, forms are things that you integrate over, right? And the chains are the things, sorry, forms are things that you integrate, and chains are things that you integrate over. And they're dual to each other. So these guys, these forms, exhibit in a way that we'll talk this down about this. You can define a set of objects called the homology group associated to forms that have big power. Similarly, the cohomology group is a statement about chains. It's a statement about chains that are the boundary of other objects, and they're dual to each other in this sense. They're paired with the integral sign, under the integral sign. Okay, so it's a really rich subject that we're only touching base on, and don't let this coordinate definition fool you. There's much more going on with these objects than just the fact that you can take derivatives with them. So we'll talk about all of these things on Friday. Yeah.